On March 21, 2022, a commercial airliner plummeted from the sky over Wuzhou, China. It hit the Earth in a near-vertical dive. Investigators rushed to the smoking crater. To understand why the plane went down, they desperately needed the flight recorders. But the sheer violence of the impact was too much. The supposedly indestructible black boxes were severely crippled and mangled. While experts agonized over extracting the corrupted data, a terrifying truth emerged. Standard black boxes max out at surviving 3,400 G-forces. In extreme supersonic crashes, they fail. Engineers needed to build a memory drive that could survive an impossible 60,000 G-forces. They tested stronger titanium and thicker foam, but everything shattered under the pressure. The industry hit a wall. That was until they looked at a tiny bird that slams its face into solid wood at 15 miles per hour. The woodpecker strikes a tree 20 times a second, experiencing forces that would instantly kill a human. Yet it never gets a concussion. Scientists discovered the bird has a specialized spongy bone in its skull that absorbs shock, and a unique bone that wraps all the way around its head like a biological seatbelt. Engineers copied this exact anatomy. They built a new flight recorder using a specialized metal foam to mimic the spongy bone, and packed the fragile microchips inside tiny glass beads. They loaded this new device into an air gun and fired it into a solid aluminum wall at 60,000 G-forces. The outer shell was deformed, but the electronics inside were perfectly intact. Their billion-dollar bullet trains were creating massive explosions every time they left a tunnel. It was loud, it was dangerous, and it was about to shut down the entire rail system. As these trains entered tunnels at 300 kilometers per hour, they pushed a wall of air ahead of them. This created a shockwave known as a tunnel boom. The noise was so loud it could be heard for miles, shattering windows and terrorizing local communities. Engineers tried everything. They tried bigger tunnels. They tried sound dampeners. Nothing worked. The physics of air resistance seemed impossible to beat. That was until Eiji Nakatsu, a lead engineer and avid bird watcher, noticed a tiny creature performing a perfect physics miracle. He watched a kingfisher dive into a lake to catch a fish. Despite the massive change in density between air and water, the bird created almost no splash. It was a master of fluid dynamics. The secret was in the specific wedge-like shape of its beak. Nakatsu redesigned the nose of the Shinkansen bullet train to perfectly mimic the kingfisher's beak. The result was revolutionary. The new trains were 10% faster, used 15% less electricity, and most importantly, they became silent. Renewable energy had a massive physics-breaking problem. The world's largest wind turbines were failing exactly when we needed them the most. Engineers built giant, perfectly smooth blades to catch the wind, but fluid dynamics is unforgiving. In low winds, the blades stalled and stopped moving entirely. In severe storms, the smooth edges created massive drag pockets that threatened to rip the million-dollar towers apart. They tried sharper edges. They tried lighter materials. Nothing worked. The laws of aerodynamics dictated that making the blades bigger only made them more unstable. The entire industry hit a dead end. That was until the year 2004, when a biomechanist named Dr. Frank Fish noticed a physics miracle on a 40-ton sea monster. The humpback whale is the size of a school bus, yet it can perform incredibly tight acrobatic turns underwater to catch tiny fish. Dr. Fish realized that aerodynamically, a creature this massive should stall and sink. The secret was on the very front edge of its fins. They were not smooth. They were covered in massive, ugly bumps called tubercles. Instead of pushing water away, these bumps sliced the fluid into spinning vortexes, locking the flow directly to the fin. When his team copied these exact bumps onto a wind turbine, the result was a total paradigm shift. The bumpy blades captured wind at incredibly low speeds, refused to stall, and increased energy production by a staggering 20%. Like this video to tell the algorithm you want to get smarter, and subscribe to Quantum Dive to see what we uncover next.